Welcome back to Radio Signals, everyone. My name is Mark, and my call sign is N9WIB. This is the Technician License Series, Lecture 8, Radio Wave Propagation. In today's presentation, we will define what radio wave propagation actually is, and then review factors in radio wave propagation, review the types of propagation, and also describe different types of propagation phenomenon. We'll introduce the solar cycle very briefly and get into it a little bit in more detail with advanced lectures for general and extra class later on. And then we'll end with defining what usable frequencies are, specifically minimum usable frequency and maximal usable frequency. So what is radio wave propagation? Radio wave propagation is essentially what happens to your radio waves once they leave your antenna and reach their destination. On your transceiver, you're going to hit the push-to-talk button. You're going to transmit. Your antenna will generate radio frequency energy. That energy will transmit or go beyond your antenna into the air and go to its final destination, wherever that may be. Radio waves travel in a straight path until they encounter an object, which may distort them, may bend them, or may reflect them. Radio waves spread out and lose strength over distance. As an example, take a very still large pond and drop a pebble in the center of that pond. You can see that there are smaller rings that form or ripples in the water that spread out from that centralized point. As they go farther and farther, they start getting weaker and weaker and less noticeable till they're no longer noticeable whatsoever. Range describes the distance over which a radio signal can be received. Same thing going back to the analogy of the rock or pebble in a pond water. Once those waves start dissipating to the point where the water is still, that's the range which was effective. Many radio waves travel less than a mile, or they can travel around the world or beyond our atmosphere and beyond. Radio wave propagation depends on the frequency of the signal, the elevation and orientation of your antenna, and also the power of your transmitter. But your antenna is going to be the most important part of the equation. Three very general types of radio wave propagation include surface wave, line of sight, and skywave. Surface waves are known as ground waves. They essentially hug or follow the curvature of the Earth. These can go beyond line of sight and beyond the horizon. This is most efficient for frequencies below 3 megahertz, and surface waves can be affected by terrain. So if it encounters a hill or a mountain or very rough terrain, the signal can be diminished or distorted, or it can also be enhanced by certain conditions, very conductive soil or by seawater. So seawater will enhance ground wave or surface wave propagation. Line of sight propagation is exactly what it sounds like. It's a little more complicated, but to simplify matters, let's use this example. So we have an example of actually 4 radio stations on the Earth, and let's start off with the smaller stations. So the smaller station to the left is going to transmit or try to transmit, let's say it's a VHF operator. It's going to try to transmit a radio signal, and it does not make it across the horizon. So it gets interfered with and does not make it to the other station across the horizon, which is here. So these signals will not get to each other. But the other 2 larger stations, the ones that have taller antennas and can see above the curvature of the Earth, above the horizon to a certain degree, will have better luck at radio wave propagation. So a signal would be easily seen between these 2 and travel line of sight from transmitter to receiver without any difficulty. So let's say there's somebody over here with a small handy-talkie. Again, I'm not the best artist. And they have an HT in their hand. But there's a big mountain here. This may be line of sight, and that person may be able to get his signal to the other person on the mountain, but that's it. So the big mountain is interfering with his signal transmission, and they can't transmit any further. But this is essentially line of sight radio wave propagation. There are two other terms utilized in describing radio wave propagation. One is reflection of radio waves, and the other one is refraction of radio waves. And these are different. So let's look at reflection first. So let's say there's a transmitter down here to the left, known as T, and that transmitter puts out a radio signal or transmits a radio signal from Earth. That signal is going to go up to the upper atmosphere, to specifically, let's say, the ionosphere. And let's just shorten it just for brevity right now, but this is the ionosphere. It's going to hit the top of the atmosphere, known as the ionosphere, and bounce back towards Earth and hit Earth once again. So this is known as reflection because it's reflected off the top of the atmosphere. And this angle right here, the incident angle, let's call it A, and the reflected angle, let's call that B, are equal. So in reflection, the incident angle is going to be equal to the reflected angle. And that's a reflected radio wave. Refraction is not necessarily reflection. Refraction is a bending of light or bending of a radio wave. So the reflection on the left is going to be more typical for your higher frequencies, like maybe 180 meters. Oh, sorry, getting confused. So 160 meters, 80 meters, 40 meters, etc. So more HF band. The refraction is going to be more typical of your VHF signals, which we'll get into in a little bit. So the radio signals are transmitted from Earth, and they go up, and they're high enough in frequency and powerful enough to actually go through the ionosphere and not be reflected back. But they are bent. So this results in refraction. So when a radio wave or even a beam of light is refracted, it is bent and not necessarily reflected. So this will actually go out into space and be transmitted to, who knows, your friendly neighborhood space alien. But that's it. So that's reflection and refraction. There is also something called diffraction. And diffraction results in scattering of radio waves behind an object. So radio waves can still be heard behind an object that they come in contact with, but they may be a little bit distorted. So radio waves are essentially scattered or diffracted off the object, and they fill the void within its shadow. This is most effective for objects with narrow or sharp forms. Constructive and destructive interference can form after a radio wave is bent or diffracted. After radio waves are scattered, they can recombine either constructively or destructively. A signal will be enhanced with a constructive in-phase pattern, and a signal will be dampened with a destructive out-of-phase pattern. So think about the analogy of the waves on a very still pond. If you drop that pebble into the pond, the waves are created. And if you would happen to drop another pebble maybe 2 or 3 feet away from that, some of those waves may combine and become larger. So that's constructive in-phase interference. However, some of those waves may actually cancel each other out. So the peak may intercept the trough of the other one and actually create a flattening of the pattern or a destructive out-of-phase pattern. Multipath is a recombination of scattered radio signals that can result in distorted or weak reception. Multipath is essentially a accumulation of radio waves that may have been refracted, may have been reflected, or they may have undergone the process of diffraction by being distorted by a nearby object. So once all those radio waves combine, either constructively or destructively, the signal can be significantly distorted or much weaker on reception. If you wanted to try to avoid multipath or at least abate it a little bit, try changing the orientation or position of your antenna, or try moving a few feet away from your current location. So let's look at constructive versus destructive interference patterns. So constructive we can have one wave or radio wave, or even water wave if you want to think of the previous example here. And then you have another wave that is generated, and it's actually the same phase. So it kind of mimics wave 1, and it's the same pattern and same phase. So the peaks align with the peaks, and the troughs align with the troughs. So this is wave 1, this is wave 2, and then they will combine to form wave 3, which will be a constructive wave and have twice the amplitude of wave 1 and wave 2. So conversely, we can have a destructive pattern where wave 1 and wave 2, let's see if we can draw this accurately. So you can see that these are exactly 180 degrees out of phase. So not exactly, because my drawing's terrible, but approximately 180 degrees out of phase. The peak here matches the trough. So the peak of wave 1 matches the trough of wave 2, and so forth. And those guys are going to combine into wave 3, which is going to have a significantly dampened amplitude, almost representing a straight line. So going back to constructive interference, the signal might appear much stronger. And with destructive interference, when the waves are out of phase, will result in a significantly dampened or weaker signal. There are some interesting phenomena that occur with radio wave propagation. Some are known as picket fencing. Vegetation has an effect on propagation. There's also something called tropospheric ducting, and precipitation also has an effect on propagation. Picket fencing is essentially a fluttering sound in your radio signal or the received signal in, let's say, your mobile transceiver. Let's say you're driving down the highway or driving down a road, and you start receiving a signal from a nearby repeater that appears to be kind of fluttering back and forth. This is due to multipath. So there are dead spots associated with multipath, and those spots are typically spaced maybe half a wavelength apart. So when you're driving through those dead spots, and you'll get a sensation of radio wave fluttering or picket fencing, especially with VHF and UHF frequencies. Vegetation can also have an effect on radio wave propagation. This is especially true of VHF and UHF signals. In wintertime, when all the leaves are off the trees, you may have much better propagation. In summertime, when the trees are just full of green foliage and vegetation, a lot of those radio signals can be absorbed. So that may limit your VHF and UHF propagation in spring or summertime. But in wintertime, it will hopefully improve. Another interesting phenomenon is called tropospheric ducting. This can occur with temperature inversions, in which the temperature of the atmosphere from ground level going up will increase rather than decrease, or with the passing of weather fronts. So let's say there's a cold front that's coming through and there's a significant differential between the warm air mass and the cold air mass. These different meteorological phenomenon will create ducts within the atmosphere. Not ducts as in quack, but ducts as in your heating and cooling duct. So a path for the radio waves to pass through. So these ducts can carry VHF and UHF radio waves well beyond the line of sight, more than 300 miles. So typically you can hear a repeater maybe 25, 30 miles away. In some circumstances, if the repeater is on a mountain, you can hear it maybe up to 100 miles. But in this case, where the radio waves actually get trapped in these atmospheric ducts, they can travel more than 300 miles. I've heard this before while driving back and forth to work. All of a sudden, you're on a certain repeater frequency and expect to hear your local repeater, which you do. But when there's no voice communication on the repeater, you actually may hear signals from another repeater in a different state that's on the same frequency. Precipitation can also have an effect on radio waves. So fog and rain can absorb UHF and microwave frequencies and thus inhibit propagation. So if it's raining out or if it's a very foggy morning and you're trying to operate on UHF or microwave frequencies, those frequencies the radio signals are probably going to get absorbed to a certain degree by the precipitation. This is not so much the case with lower frequency modes such as HF and lower VHF frequencies as well. Now a topic that's very interesting to all amateur radio operators. Ham radio operators get very excited about solar activity and solar cycles. So this graph depicts the average solar cycles from the year of 1913 and through a predicted 2031. So right now we're getting into solar cycle 25, which is very exciting. So as you can see from the graph, the solar cycles increase and decrease by a range of 11 years. So every 11 years, a new solar cycle forms. And you can tell that some solar cycles were more active in the past than others. Unfortunately, the last few solar cycles haven't been the greatest. But this solar cycle is still up in the air, but there's some evidence that it may be a slightly better solar cycle than the previous one. And this is solar cycle 25. So why are we all excited about solar cycles and solar activity? Because the more sunspot activity, the more activity in the sun, the more ultraviolet radiation that's generated, and that will actually increase or enhance radio propagation. So increased solar activity increases ultraviolet radiation from the sun into our atmosphere and causes increased propagation. Specifically, the ionosphere is the level in the Earth's atmosphere that has the most benefit from the UV rays. The ionosphere is from 30 miles from the Earth's surface to 260 miles above the Earth's surface. So if we take that into a little bit of context, 30 miles is maybe the width of a very large city. Let's say the city of Chicago. So that would include the width from the lakeshore to the far western border and maybe a little bit including a few of the western suburbs. So it's not that much. It may take you about an hour to drive that in linear distance depending on traffic. As opposed to the height of the ionosphere, which is around 260 miles above the Earth's surface, that is approximately equal to the width of the state of Wisconsin in certain locations. So we can see that it's not that far. So our atmosphere the ionosphere is not that far above the level of the Earth's surface. And below the ionosphere, of course, at the bottom layer is the troposphere, and above that is the stratosphere. And those are the levels that aircraft fly in and most of the weather occurs. The ionosphere is a portion of the atmosphere where the air is very thin and mainly composed of oxygen and nitrogen in lower concentrations, given its distance away from Earth. But the oxygen and nitrogen are actually ionized by the ultraviolet radiation from the sun. And when the oxygen and nitrogen are activated or ionized, that increases the ability for the atmosphere to reflect radio waves. The ionosphere is just not one layer, but it is divided into multiple different layers. The layer closest to the Earth is called the D layer. The next layer up is the E layer. And finally, there is an F1 and F2 layer at the very top, or the farthest portion away from the Earth's surface. The F1 and F2 layers are distinct layers within the daytime. However, at nighttime, they may form into one single F layer. The E and F layers can refract and reflect radio waves. So when radio waves are produced on the surface of the Earth and they go up through the ionosphere to the E and F layers, those layers can bend some radio waves and allow them to pass out in space, and the other radio waves are reflected back down to Earth. The D and E layers, which are closest to the Earth's surface, can absorb radio waves. So that's good news and bad news. Mainly bad news for the HF frequencies, the lower bands during the daytime hours. So daylight increases ionization and nighttime decreases ionization. So obviously the sun is active during the daytime. That's what produces the daylight. And ionization is most active during the daylight. And that will have most of the radio waves reflected back to Earth in the upper layers. But nighttime, it's a different story. So ionization decreases and the ability for the ionosphere to reflect radio waves decreases at night. For the ultra-high frequency and very high frequency radio waves, the higher frequencies tend to pass through the ionosphere into space and are refracted. So they're bent but not reflected back down to Earth. In some cases where you have a very active solar cycle at the very peak, sometimes those radio waves can actually be reflected back down to Earth, increasing UHF and VHF propagation, probably mainly VHF propagation, not necessarily UHF. But typically these radio waves just go straight out into the atmosphere and pass through the ionosphere into space and don't come back to Earth. So there's really no long distance UHF and VHF propagation as a general statement. Occasionally, there are patches of the middle layer, the E layer of the ionosphere, which can be ionized enough to actually reflect VHF and UHF waves back to Earth, dramatically increasing the propagation distance. This is occasionally, and I say patches, so it does not happen all the time, and it does not happen throughout the entire continent or the world. It only happens in patches. This is known as sporadic E, and this occurs most commonly in early summer and midwinter if you're lucky enough to catch it. As mentioned previously, the D layer of the ionosphere disappears with nightfall, but the D layer is very active during the daytime. The D layer absorbs the frequency and wavelength of around 160 and 80 meters, these radio waves, and inhibit propagation. So during the daytime, the D and E layers are active and they absorb the 160 and 80 meter band. So you're not going to get much activity on 160 or 80 meters during the daytime. However, when night falls, the D layer will go away, and those radio waves, the 160 and 80 meter band, will be able to travel farther and not be absorbed and actually reflect off the combined F1 and F2 layers and come back down to Earth and be reflected and go on very long distances. So that's your HF frequency and long distance propagation. That's your DX propagation, which means long distance. All right, let's take another example for radio wave propagation. As you can see, we have the Earth in green at the bottom and 2 radio stations. And then we have the layers of the ionosphere, which is from 30 to 260 miles above the Earth's surface. The lowest layer of the ionosphere is the D layer, then the E layer, and then the F1 and F2 layer. And remember that the F1 and F2 layer will combine at night into a single layer. The D layer will be active during the daytime, but will dissipate and go away at night when there's decreased UV solar radiation. And the E layer is just kind of someplace in between. So let's take the far right radio station, the antenna. That radio station, let's call that a VHF radio station, or UHF. And let's see what happens when a signal is transmitted. So this station is going to transmit its signal into the atmosphere. And it's going to go through the D layer. It's going to go through the E layer. It's going to go through the F layer. Oh, what happens? We're starting to bend a little bit. We're bending, so we're refracting, but we're still going out into space. So those waves are high enough frequency and high enough energy where they're going beyond the ionosphere. They're not really being affected by the ionosphere except for a little bit of refraction, not reflection, but they're being bent in the F and F2 layers, F1 and F2 layers, and being bent out into space. So they do not get reflected back down to Earth. But there are those crazy circumstances when you might be at a peak solar cycle or sporadic E where some of that VHF energy might be reflected back down to Earth. But for the most part, it goes out into space and does not come back down. That's why VHF is only good for repeater and line of sight communication with another antenna. So for HF communication, let's pretend this red tower on the left is transmitting at night. And let's say he or she is transmitting on 160 to 80 meters. So they're transmitting out their long waves. And all of a sudden it starts getting... Well, actually, let's do the daytime. So this transmitter's transmitting during the daytime where the D layer is active, but that 80 meter and 160 meter signal is getting absorbed and it's not going anywhere. So 80 meters and 160 meters is really not active during the daytime because it is being absorbed by the D layer of the ionosphere, which is being ionized by UV radiation. So no go on the 80 to 160 meter bands in general. However, if the nighttime occurs and the D layer starts going away and that station tries again and starts to transmit the longer waves, it'll go past and hit the combined F layer and be reflected back down to Earth. And it's still that same frequency. I just can't draw that well. So let's say this station is in, let's say the station's in New York, and this station is in England. So it's actually going across the Atlantic. It's going from the station, going up to the F layer, and being reflected back down to Earth. And that's considered one hop. So that's one hop. And you can see how HF propagation is long distance. So that's called DX, or distance communication. However, the Earth can also be reflective. So that signal can be bounced off, especially the salt water, and go all the way back up to the ionosphere, to that F layer at night, and be reflected again back down to the Earth. And let's say that now it hits Russia. and let's say it bounces back up. So as this happens, as distance is increasing, the signal is getting weaker and weaker and weaker as it travels more and more distance. But it's going back up into the ionosphere and again bounces back. So it's taking, 1, 2, 3 hops. And let's say it ends up in California. So that went from New York to England to Russia to California, all with several bounces back and forth between the combined F layer and between the Earth's surface. So that took about 3 hops. And there's a phenomenon where there can be really long path propagation, and that signal may actually come right back around the Earth's surface and come back to you by something called long path. So you actually may hear your signal come back to you if propagation signals conditions are right, and you may actually hear that your own station again, maybe a few milliseconds or a small little echo in your signal, and you may hear it come back to you. So those are the basics of propagation with HF and VHF and UHF communication and the different layers of the ionosphere. Now we can take another approach as to defining which frequencies are going to be workable for HF transmission or just transmission in general. So there's something called the LUF, or the lowest usable frequency, and the MUF, the maximal usable frequency. So the lowest usable frequency, as an example, let's say it's the daytime and we want to transmit on 80 meters. And our antenna station is right here. And we get our HF rig out and we start transmitting on 80 meters at, let's say, noontime. So here's our 80 meter signal. It's being transmitted long wave, and all of a sudden we hit the dreaded D layer of the ionosphere because it's noon and there's lots of UV light out, and that 80 meter signal gets absorbed, doesn't go anywhere. So that's not a usable frequency. Okay, so let's try 40 meters. So we're increasing in frequency, increasing in the energy of the wave, and let's try transmitting. Maybe it gets a little farther before it peters out, and let's say that it gets absorbed as well. Okay, let's go up to 20 meters. So 20 meters, we try transmitting, and the wavelength is a little shorter, has a little more energy, and lo and behold, we hit the ionosphere, and what happens? Oh, we're coming back down, so it's reflected. So we're actually in business. So 20 meters is a good wavelength to use, and that should be considered your lowest. It'll be 20 point something. The frequency is obviously going to be 14 point something megahertz, but let's consider the 20 meter band as our lowest usable frequency. Okay, so lowest usable frequency is 20 meters because the lower bands, 80 meters and 40 meters, we're out of luck. It's being absorbed by the D layer in the middle of the day. But 20 meters goes to the ionosphere and bounces off. So let's try some VHF. Well, let's start off with, let's go to 10 meters. So let's have the transmitter, let's move it over here. Let's get another antenna and go to 10 meters. Let's say it's the very early solar cycle 25, and we tried 10 meters during the daytime. And the ionosphere still isn't strong enough to bounce that 10 meter signal back. So it's going to bend, refract, and go off into space someplace. So above, we can't use for long distance communication, we cannot use anything that is going to be higher than 10 meters in frequency. So VHF, UHF will obviously go through the ionosphere, be refracted or bent, and go out into space. So someplace between 20 meters and, let's say, 10 meters, let's try 17 meters. And 17 meters, let's say we try that. And it actually works. It bounces back and comes back down to Earth. So just to round things off, 17 meters will be our maximal usable band with its appropriate frequency. So we can say that's the MUF, or maximal usable frequency, and this is the LUF, or the lowest usable frequency. So anything lower than the lower usable frequency is going to get absorbed in the atmosphere. Anything higher than the maximal usable frequency will penetrate the ionosphere, be refracted, and go off into space. Everything else between the LUF and the MUF will work just fine and bounce off the ionosphere, and you should have good luck with DX communication. Another important concept is the concept of skip. So let's say we're in New York and we're transmitting on 40 meters. So the radio wave is going to go up to the ionosphere and bounce back. And let's say it's going to travel all the way to France. But you can see that it traverses the ocean, but it skips Iceland. So this is known as the skip region right here. So any type of station between New York and France within a certain distance is not going to hear the signal. But New York and France should hear each other's signals because they're bouncing off the ionosphere. But the region such as Iceland or Greenland are in that skip zone, and they're not going to be able to receive any signal. Another interesting propagation method in amateur radio is due to the auroras, or northern lights. The northern lights are essentially sheets of charged atmospheric particles 50 miles or above Earth's surface in the ionosphere. And they're not there all the time, but they correlate with the solar activity. And in times of increased solar activity, then the auroras are more likely to occur. I've seen this once or twice in my lifetime, and they're absolutely beautiful. I've never seen anything more beautiful in my life. These auroras and the charged particles within them can reflect VHF frequencies and increase propagation well beyond the typical VHF range. However, as you know, for those of us that have seen the auroras, they are dynamically changing, and the radio signals that actually get bounced off the auroras come back to Earth or your receiving station, therefore are going to be a little bit distorted and also change in signal strength on a fairly constant basis. Meteor scatter is actually another neat phenomenon. Meteors leave trails of ionized gas in the E region of the ionosphere when they enter the atmosphere. And you can actually bounce radio signals off this ionized gas back to Earth, and this is known as meteor scatter. The best band for meteor scatter is 6 meters. And you can reach communication distances of anywhere from 1,200 to 1,500 miles. So that about wraps it up for this presentation on radio frequency propagation. We hope you guys have learned a lot and have fun. 73. And don't forget to like our channel on YouTube, and also hit the subscribe button and hit the like button. And go to radiosignals.org if you feel like contributing and supporting us. Thanks so much. See you next time.